Welcome to the penultimate lecture in this term's philosophy of physics colloquium. 10 years ago, after some Skype conversations and email correspondence about general relativity and alternative theories of gravity, I was invited by today's speaker, then a departmental lecturer here in the philosophy department, to visit him in the philosophy of physics group. For me, that was a turning point, and I decided to pursue a professional career in philosophy of physics. This makes today's lecture very special for me and the speaker, also because the greater part of my own work, including my DPhil thesis, was and continues to be significantly influenced and inspired by his work. He is someone who embodies an ideal, my ideal, certainly, for philosophy of physics, one that combines impressive historical erudition, philosophical acuity, and square engagement with the problems in physics that really matter. And I refrain from commenting on his exceptional qualities as a teacher and mentor. It is therefore my extraordinary pleasure and Oxford's great privilege to announce as today's speaker, Professor Dennis Lehmkuhl from the University of Bonn in Germany. Professor Lehmkuhl studied physics and philosophy at Hamburg in Germany and Imperial College in London before embarking on a DPhil at Oriel College under the supervision of Oliver Pooley, Harvey Brown, and Jeremy Butterfield, with a seminal and wonderfully rich DPhil thesis in 2009 on space-time matters, on supersubstantivalism, general relativity, and unified theories, field theories. After various academic positions, in particular a junior professorship at the University of Wuppertal, a research professorship at Caltech, a departmental lectureship at Oxford, and as a contributing editor at the Einstein Papers Archive, he was appointed in 2018 the Lichtenberg Professor for History and Philosophy of Physics at the University of Bonn. There he has established Europe's leading center for the philosophy of space-time and gravitational physics. Professor Lehmkuhl's work focuses on theories of gravity, space-time structure, and how they interact with matter, with a particular interest in the analysis and interpretation of black hole physics and gravitational wave physics. Of his research publications, I'd like to draw your attention to 4 that I find particularly eye-opening and inspiring. A paper from 2014, Why Einstein Did Not Believe That General Relativity Geometrizes Gravity. In 2013, with Harvey Brown, Einstein, the Reality of Space and the Action-Reaction Principle. In 2020, a 2-part paper series questioning the matter-space-time distinction together with Niels Martens. And very recently, in 2023, a paper so nice that I'm quite jealous, on the epistemology of observational black hole astrophysics, together with Juliusz Dobaszewski. Today's topic, however, is going to be Einstein's 6 paths to the metric tensor and why he interpreted it differently than you do. Thank you very much, Dennis, for kindly accepting our invitation to speak here today. It is an honor and a pleasure to have you here. Ganz herzlichen Dank.
Thank you, Patrick. That was way, way too kind. And well, thank you, everybody, for coming. I'm really, really glad to be back in Oxford and to be interacting with all of you. Thank you. Yes, I'm going to talk about Einstein's path to the metric tensor. So the mathematical object that, if you want, forms the foundation of general relativity. And the Nestor of Einstein's scholarship, John Stachel, argued that at least the early history of general relativity can be thought of as a drama in 3 acts. The first act centers around Einstein's discovery of the equivalence principle in 1907. The second act centers around his idea of representing gravity by a metric tensor and thereby linking it to the non-Euclidean nature of space-time. And the third act centers or leads up to November 1915, when Einstein found what we today call the Einstein field equations. And much of Einstein's scholarship has focused on the transition from 1913 to 1915. So from the point in May 1913, when Einstein essentially had the research program laid out in front of him, thought that the right thing to do was to search for a theory of gravity that represented the gravitational field by the metric tensor of a four-dimensional spacetime, that would have generally covariant field equations, of which the energy momentum tensor would be the source term. So that research program, that blueprint of how the theory should look like, Einstein had in May 1913. And much of Einstein's scholarship has focused on the question of how he got from there to November 1915, when he actually found the Einstein field equations. And that's a beautiful adventure story. And one reason why so much of the scholarship has focused on this 2-year period, though, is, as so often in history, because of the source material. John Norton in the 1980s found the notebook, now called the Zurich notebook, that Einstein used while searching for this theory of gravity, right? And, you know, if you have good source material, then you can really do history properly, detailed analysis. And that's what Norton, Stachel, Janssen, Sauer, Wren, and collaborators did. Much less work has been done on the period leading up to May 1913. So the point when Einstein transitioned from what used to be a scalar theory of gravity to a metric theory of gravity. And in a way, I think, I mean, this is a beautiful story too, but philosophically, how he got to this research program, of which the Einstein field equations are the fulfillment, is in a way even more philosophically interesting, because it suggests that there is a sort of ontological jump from a particular type of theory to another type of theory. And so this is what I'm going to focus on in the talk today, how Einstein got to the point of May 1913, where he had the research program finished that would be completed in November 1915. So the document, why do I keep referring to May 1913? That's when Einstein and Marcel Grossmann published this paper, in fact, published as a booklet because it's a rather long paper, which was called The Entwurf to a Generalized Theory of Relativity and of Gravitation. Entwurf is blueprint, plan, or draft, right? So it's very clear in how they put it that they don't see this as the final theory. At best, they see this as a first step, as a blueprint, a draft of what they expect the general theory of relativity to be. But again, much of what will be general relativity is already in that Entwurf paper of 1913. In fact, so much that one could ask whether the crucial ontological philosophical change in Einstein's thinking took place between February 1912 and October 1912, because in February 1912, Einstein wrote down two theories of gravity, or one if you want, but two sets of field equations, a theory of gravity in which he defined a scalar gravitational field defined on a three-dimensional manifold representing space. So that was clearly supposed to be a theory of the gravitational force, scalar force field defined on a three-dimensional space, and that was his theory of gravity in 1912. And in October 1912, he and Grossmann start working on what would become the Entwurf theory, which would take them half a year. But already in October 1912, it is clear that they're looking for a theory based on the metric tensor of a four-dimensional space-time manifold, and that they identify the gravitational potential with that four-dimensional metric. So one might think that there is a major ontological change here between February 1912 and October 1912, two very different types of theory, one a force theory of gravity, and another one that reduces the gravitational force to the geometry of space-time, and also transitions from a theory of space to a theory of space-time. And what I want to convince you of in this talk in the next 45 minutes or so is that this impression that one gets from just looking at these sort of base mathematical objects that feature in the theory of February 1912 and of October 1912 can be very, very misleading, right? This seeing just from the, one is a theory of space-time, the other is a theory of space. One interprets gravity as a force, the other one interprets it as a feature of space-time. Clear ontological differences. What I'm going to argue is that from Einstein's perspective, this was not at all the case, and that there is a much stronger sense of continuity from this kind of theory to this kind of theory, which led him then to resist this geometric interpretation of general relativity. And so this brings me to the three puzzles that I want to answer in this talk. The first is, given what I just said, how did Einstein come to the idea to develop a theory of gravity that is based on the ideas of associating gravity with a metric tensor, for which he wanted to find generally covariant field equations and have the energy momentum tensor as its source? Then how did he interpret the metric tensor? And what does his interpretation with the metric tensor have to do with geometry, geometry of space, geometry of space-time? Because clearly it has something to do with it, despite of what I just said. The question is just, what exactly is Einstein's interpretation of the role that geometry plays in general relativity? And third, what can we learn from all this, not just historically, but also philosophically? I'd be perfectly happy just learning something historically from it, but I actually do think that there is a philosophical lesson to it. And just to give you a tease of it, I think part of it is that just looking at the mathematical structure of the end result of a theory is really just the surface structure. And that if you look at the context in which a theory was discovered, a whole plethora of different interpretational possibilities show up in front of you. And some of them might actually be good philosophical options. And even if they're not, at least seeing these different interpretational possibilities will open your eyes to the possibility that you can't just read off the ontology from the base mathematical structure, but that more is needed to at least decide between different interpretational possibilities. Okay, so that's the aim. And the structure is starting out from February 1912. So I'm going to tell you in detail about the two scalar theories of gravity that Einstein developed in February 1912. That's our starting point. And the question is then, how does he get from there to the metric theory of gravity, or the project of a metric theory of gravity that he embarks on in October 1912? And I'm going to argue that there are 6 paths rather than 3 acts, right? 3 acts suggest a kind of linearity. I think Einstein, essentially in these 6 months, walked on 6 paths in parallel, and in a way the path started approaching, and all 6 of them brought him to the idea of a metric tensor theory of gravity. The first path depends on an analogy between gravitational and inertial fields on the one hand, and electromagnetic fields on the other hand. The second path comes out of Einstein considering the equations of motion that a massive particle subject to gravity would feel. Because throughout his life, the question of what the equations of motion of a particle subject to gravity are was equally important to him as the question of what the field equations for the field itself are. So that's the second path. The third path comes from detailed investigations in the special relativistic development of mechanics that come after 1905, where Einstein was not the leading figure. And Einstein, in fact, both here and there, Einstein draws on major work of his contemporaries. On track three, he looks at the works of the question of what the concept of a rigid body is in general relativity, in special relativity. And that path and the mathematical methods that are being developed in trying to answer that question, in particular by Born and by Sommerfeld, give him a third path towards the metric tensor. The fourth path is what John Stachel, in his way of thinking about general relativity as a drama in 3 acts, called the missing link, the explanation of how Einstein got from the scalar theory to the metric theory of gravity. Namely, Einstein thinking about what would an observer on a rotating disk feel, and what does that have to do with gravity. And I do think this is a very important part of the story, but I also think it's not the only explanation, but it's one out of 6 elements. The fifth path towards the metric tensor, again, is Einstein drawing on developments in special relativity, in special relativistic mechanics, in particular due to Max von Laue, who developed special relativistic continuum mechanics, and in the course of that also what we today call an energy momentum tensor. And the properties of that energy momentum tensor suggested, again, a different path towards the metric tensor for Einstein. And finally, this now is in the summer and autumn of 1912, when Einstein moves back from Prague to Zurich. Much of this happens while he is a professor in Prague. And then in the summer, in August of 1912, Einstein moves back to Zurich to become Minkowski's successor in the chair of theoretical physics there, and rekindles his relationship with his old school friend Marcel Grossmann. And Grossmann alerts him to what was then called Ricci calculus, which we would today call tensor calculus. And one part of the story that I'm only going to touch on is that in the course of Einstein and Grossmann working together, Grossmann actually made major mathematical advances in developing what we today call tensor calculus, in which he brought together developments of Ricci and Levi-Civita on the one hand, and of Sommerfeld's vector analysis in a special relativistic context on the other hand. And all of that Einstein could profit from, and this gave him another path towards the project of a metrical theory of gravity. So that's the overall story, and I'm going to keep coming back to this graph. Okay, first, the starting point, Einstein's two scalar theories of gravity of February 1912, and how he got to them, and then how does he go on from there. So first I have to motivate how he gets to February 1912, and for that, I have to tell you about where he starts this journey, which is in 1907, when Einstein is still a patent clerk in Bern, after having failed to get an academic position directly after graduating, became a patent clerk in Bern through the help of Grossmann, which we'll meet again. And in 1907, Einstein was asked by Johannes Stark to write a major review article of the state of special relativity and special relativistic mechanics. And that necessitated for him to think about special relativity in a way that put it into a new framework and also summarize what had been done since his first paper in 1905. And he saw in front of him that he needed to take care of two construction sites. He believed he had to solve two problems. The first problem was he believed that he needed to find a theory of gravity that is compatible with relativity theory, because Newton's theory of gravity and Einstein's special theory of relativity are inconsistent with each other, partly because Newton's theory presupposes that simultaneity is absolute, and partly because it also presupposes that the gravitation interaction propagates at infinite speed, which establishes an absolute sense of simultaneity. So one of them had to go, and maybe not surprisingly, Einstein believed that Newton's theory of gravity had to go, and special relativity was there to stay. That was the first construction site. Find a new theory of gravity that is compatible with relativity theory. The second, and this, by the way, this is something that the majority of the community at the time agreed on. Many other people were also embarking on finding a solution to this problem and trying to develop a new theory of gravity that was compatible with special relativity. The second construction site, only really Einstein saw at the time. Yeah.
Who was the rest of the community?
Well, mostly Planck, Laue, Abraham, me, I think it's a small community. German-speaking people who had read relativistic, the first relativity paper. Starting from Planck. Planck was a strong endorser, and Planck basically gave lectures on special relativity already in 1906. Through Planck, Laue got interested, and other people. But it's still less than 10 people. But that's a sizable amount of the German theoretical physicists at the time.
And very quickly, in the mathematical side, were there already Lorentzian signature geometries on the scene or no?
I don't think so. But if so, they had not entered physics. Yeah. 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 Okay. Well, apart from Minkowski's spacetime, of course. Yeah, Minkowski. Yeah, that's Lorentzian signature. Yeah. Okay. So the second construction site that Einstein saw is that he wanted to extend the relativity principle from just relating inertial motions to it relating arbitrary types of motion. And this is in direct connection to Leibniz, who we don't think Einstein read in the original, but Mach he did read in the original. So the idea that not just inertial motions and whether we're at rest or moving at a constant speed should be a question of the frame of reference, but every type of motion. So it should be possible to transform, to find transformations that would transform you from being accelerated to being at rest. And it should just be a matter of your coordinate system or your relative motions, whether you consider yourself as at rest or as accelerated. And this, especially the reading of Mach, who also endorsed this, allowed for an idea that would become very important for Einstein. Namely, one of the things he found in reading Mach was that inertial forces, just like gravitational forces, are due to the interaction of massive forces, of massive bodies with each other. So in a way, just like gravitational forces have a source, namely the mass of bodies, we started to think, well, inertial forces should have a source too. And that brought gravity and inertia for him closer together, and the concepts of gravitation and inertial forces. And eventually this gave rise in 1907, published in this review article of 1907, to what he called the most fortunate thought of his life, namely the idea that the two construction sites find a new theory of gravity that is compatible with relativity, and find a theory of the full relativity of motion, that those two construction sites are connected to each other. And they are connected by what Einstein called the equivalence principle, which is a thought, or has its first manifestation as a thought experiment. It says, well, because inertial and gravitational mass are numerically equivalent, there's no way for an observer to distinguish between the case where he's just sitting in his office in the patent patent office in Bern and being subject to a homogeneous gravitational field, versus him being out in open space or in an elevator being accelerated with 9.81 meters per second squared upwards. For the observer, at least if he doesn't have a window, there would be no way to distinguish between the two scenarios. Nor, and this is actually the one that we find in his writings in the early 1920s though, there is no way for an observer to distinguish between the case where he's falling from the roof of a house and the gravitational force and the inertial force cancel each other out exactly, so there's no effective force acting on him, versus him being out somewhere in space and there's no forces to start with, canceling each other out or not. And so this is how he put the equivalence principle in 1907 and in 1911. He said, homogeneous gravitational fields and uniform accelerations are indistinguishable. There's no way for an observer to distinguish whether he's subject to a homogeneous gravitational field or to a uniform acceleration. In 1914, he put this in a more ontologically charged way. He said, gravity and inertia are wesensgleich. Wesensgleich is one of those German words that are very difficult to translate. Essentially means gravity and inertia are the same at the very core. They're two aspects of the same thing. They're essentially the same. They're the same in their essence, intrinsically connected. And that would be the guiding idea of Einstein's career, that gravity and inertia are intrinsically connected. Of course, now, if you think about it, this has a major consequence, right? If you take this indistinguishability between gravitational forces and inertial forces to its logical next step, it brings about a breakdown of the distinction between real gravitational forces on the one hand and inertial fictitious forces on the other hand, that are just where inertial forces are typically thought of as just being due to an accelerated frame of reference, versus gravitational forces are supposed to be real forces that originate from a source, whereas inertial forces are not supposed to originate from a source. This distinction, or this distinction between inertial forces on the one hand and real forces on the other hand feels more strong in German than it does in English, because in German the word, and that's how Einstein would have learned it, the word for inertial forces is Scheinkräfte, apparent forces. So any conceptually thinking physics student, as Einstein clearly was, who studies in physics in German, might be puzzled. Why are those forces that we feel equally much as gravitational forces? Why are they supposed to be apparent forces, and these other forces are real forces? And so Einstein's equivalence principle arguably leads to a breakdown of that distinction. Here's how Pauli puts it in his 1921 textbook, and there's similar quotes from Einstein, though not as succinct. He says, in Einstein's theory, gravitation is just as much a fictitious force as the Coriolis and centrifugal forces are in Newton's theory. However, it is equally justified to say that in Einstein's theory, neither of these forces is a fictitious force. So the distinction breaks down. And of course, if you remember, Newton had famously defined or justified the existence of absolute space by reference to inertia forces that he took as signifiers of real motion relative to absolute space. And one major question is then, if the distinction between real and inertia forces breaks down, what does this mean for the existence of space? Okay, we'll come back to that. So first, this is the context of Einstein's development of the equivalence principle. Now, how did he use it? Because that's something that hasn't been appreciated. That's one of the things that hasn't been appreciated enough. First and foremost, for Einstein, the equivalence principle was a tool, something to work with. And he did that in particular in his papers of 1911 and 1912. Between 1907 and 1911, he basically worked entirely on other things, thermodynamics, statistical mechanics, quantum theory, and he came back to the topic of gravitation in 1911, and then with full force. And so in these papers of 1911 and 12, Einstein defines a precise version of the 1907 equivalence principle with clear mathematical reference of the term homogeneous gravitational field on the one hand, and of uniform acceleration on the other. Drawing, by the way, on work of Max Born, who introduced a new notion of acceleration into special relativistic mechanics. And drawing on this, Einstein uses the equivalence principle as a tool and again follows the following schema. First, he asks a question about how a homogeneous gravitational field would influence this or that physical process, right? Does the presence of a homogeneous gravitational field have an effect on the path of light rays? Does the presence of a homogeneous gravitational field have an effect on how clocks tick, and so on? Then, using the equivalence principle, he transforms this question into the question of how uniform acceleration would influence this physical process. Given that special relativistic mechanics is a worked out theory, that's something he can operate with. So he does the calculation in special relativistic mechanics, and then using the equivalence principle, he argues that the same prediction also applies to homogeneous gravitational fields. So the use of special relativistic mechanics plays a major role here. He again and again transforms questions about gravity to questions about accelerations, and then translates them back to the gravitational context. And in that context, already in the 1911 paper, he makes predictions about the influence of gravitational fields on light rays passing by the sun, on gravitational time dilation in clocks, and on gravitational redshift. Not quantitatively correct, but clear predictions based entirely on the equivalence principle. Now, quite soon, Einstein would do what I think is one of his favorite moves, something that he does over and over again in his life, namely, to claim that if two things are strongly correlated, then just identify them. If they're so strongly correlated, then they're probably the same thing in two different guises. So in the context of the 1911 paper, Einstein found that the speed of light depends on the gravitational potential, and that the second postulate of special relativity, right, the constancy of the speed of light, therefore is only valid in a limit, namely the limit when the gravitational potential is constant. So special relativity now becomes a merely effective theory that is only valid in the limit of constant gravitational potential. And the gravitational potential, of course, is a scalar field defined on 3 space. And through the dependence noted, the speed of light becomes a scalar field too. Right now, the value of the scalar of the speed of light can differ from point to point. And so Einstein poses himself the question: so maybe if the speed of light depends on the gravitational potential, maybe doesn't just depend on it, maybe it is the gravitational potential. It's a major leap, right? If there's such a strong potential, maybe there's nothing to the speed of light but being the gravitational potential. And that's then his starting point that leads him to the scalar theory of 1912. He looks for field equations that govern the local speed of light, which is at the same time the gravitational potential. In order to get there, though, he has to come back to the aims of construction side construction side 2, namely find a generalization of the relativity principle, right? And he thinks clearly the special principle of relativity is fulfilled, manifested through the Lorentz group. Generalizing the relativity principle means going to a bigger group that contains the Lorentz group as one of its subgroups. So that's what he starts searching for. Guided by the equivalence principle, he tries to find a group that allows him to transform from uniformly accelerated systems to inertial systems, including rest. And he finds such a group in the 1911 paper. Then he considers the acceleration vector that shows up in this construction as an acceleration field and uses, again, the equivalence principle to transform to an equivalent gravitational field. So that's the language he uses at the time. He keeps speaking about acceleration fields on the one hand, gravitational fields on the other hand, and the big project is to find a theory of a unified gravitation acceleration field, an analog to the unification of electric and magnetic fields in electrodynamics. Okay, so he finds a particular gravitational field. If you want a particular solution, particular way the gravitational field can be, and then he looks for the field equations that has that solution in its solution space. That, again, is also a kind of move that he does again and again, including in 1917. He has the Einstein solution of a cylindrical universe first, and then he looks for field equations that have that solution in its solution space. Same here in 1912. Now, at this point, as I said here, both the acceleration field and the gravitational field that he defines are fields defined, in this case, vector fields, 3 vector fields defined on 3-dimensional space. And given that we're here in 1911, 1912, you might well ask, so why does he not formulate this, as his big rival Abraham did, as a theory in space-time? Why does he not look for a special relativistic theory of gravity? And part of the reason was that, indeed, as Einstein wrote to Sommerfeld, he was a bit put off by the over-mathematization in Minkowski. But in other sources, he also says it's a beautiful representation. It's really valuable. So why did he not embrace it and write his theory as a theory in 4-dimensional space-time? The answer is physics. Because we see from Einstein's very polemical fight with Max Abraham in 1912, that Einstein saw the Minkowski space-time concept as intimately connected to taking the Lorentz group as the invariance group of the theory, right? And in fact, this is entirely in line with how Minkowski presents this in his 1908 paper. The Minkowski space-time is a mathematical expression of the physical fact that everything is invariant under the Lorentz group. So it was not at all unreasonable to think, well, if I'm operating with this space-time concept, I'm tethered, I'm shackled to taking the Lorentz group as the fundamental group. And of course, Einstein wanted to go beyond the Lorentz group. He wanted to find a more general group. And so he thought the progressive thing to do, the modern thing to do, is not to work in a space-time context, but to work in a 3-dimensional context and go to a bigger group and not let himself be weighed down by the concept of space-time. Of course, he would later reverse that stance, but I'm just saying at the time, I don't think this was at all unreasonable. Okay, so this brings us now to Einstein's scalar theories of 1912, what he achieves there. So his ansatz is to use the equivalence principle to find the gravitational field corresponding to uniform accelerations, and then find the field equations that allow for this field as a solution. And this is the field equations that he finds. The left-hand side structurally is completely the same as the left-hand side as the Newton-Poisson equation. You have a gravitational potential and Laplacian applied to it. The only difference here on the left-hand side is that here the gravitational potential is also the local speed of light, right? Mathematical structure the same, but the gravitational potential has an extra role to play in contrast to Newton. The right-hand side has two bigger differences to the Newton-Poisson equation. On the one hand, the source, sigma, is not just the mass of the bodies in the universe or of the given region, but it's mass energy. And Einstein spends, in fact, quite a bit of real estate in publications at the time arguing that because of special relativity, not just mass, but every form of energy has to be a source of gravitational field. So mass energy is the source of his new gravitational field equation. The other big difference is that the gravitational potential also appears on the right-hand side. That's also different from Newton, right? In Newton, you only have Laplacian of the gravitational potential on the left-hand side, coupling constant times source. And for Einstein, the gravitational potential also appears on the right-hand side. And these are the equations of motion of a particle subject to the gravitational force field that he derives in the first 1912 paper, which he also shows has the Newtonian equations of motion as a limit for motion that is where the velocities are small compared to the speed of light. So essentially, you have a modified version of m times a on the left-hand side, and then the derivative of the gravitational potential on the right-hand side. That's the gravitational force. Then, however, this change, what I pointed out here, that the gravitational potential shows up on the right-hand side of the field equations, ends up causing major problems for Einstein, because he finds that if he takes these field equations and these equations of motion, then the two of them together imply that momentum is not conserved. And so he thought, okay, so that can't be, momentum has to be conserved. So either the field equations or the equations of motion have to be changed in such a way that there's no contradiction with conservation of momentum. And then he interestingly opts for keeping the equations of motion and to modify the field equations to this form, right? So you still have the same left-hand side. This is still the same term as before. And now he has an extra term here on the right-hand side, which is exactly the term that is needed to restore conservation of momentum. So that's how he derives it. If you put that in, conservation of momentum is ensured. But he manages, there's also something that happens again and again, especially in the first 20 years of his career, something that might have been thought of as a major disadvantage, namely making the field equations quite a bit more complicated. He turns that into an advantage by arguing, well, actually, here are two arguments for why this term here should be interpreted as the energy of the gravitational field itself. So that now I have here the material source term of the gravitational field, and here the term that corresponds to the energy of the gravitational field itself. Because of course, just like the electromagnetic field, the gravitational field has to have energy too. And because every form of energy is a source of gravitational fields, the energy of the gravitational field has to be source too. So he says, excellent, this is now my new theory, more complicated mathematically, but physically more attractive. And these field equations of February 1912 already, even though they're a scalar theory of gravity defined on 3 space, already have many of the properties that we later find in GR. First, they have a representative of the energy of the gravitational field in a way better than in GR because it actually appears in a very visible way in the field equations. Second, for that very same reason, they are nonlinear. Third, the gravitational field is read by clocks because the clock ticking rate depends on the gravitational potential. And therefore, a clock can be interpreted as a device measuring gravitational fields. So there is already a sense of linking chronometry, at least here, to the dynamics of the gravitational field. Come back to that. Okay, so now we're here. Einstein's scalar theory of gravity of February 1912. Now, how does he get from there to the metric tensor, or to the program of finding a metric theory of gravity in 4-dimensional spacetime? The first track is, as I said, an analogy to the to electromagnetic theory. And this is something very important that hasn't been quite appreciated. There's not much literature on that scalar theory at all, but even the one that is there is not fully appreciated, that this was never intended to be a full theory of gravity. In fact, what Einstein saw himself as searching and as finding was the gravitational inertial equivalent to Gauss's field equation for static electric fields. So he found one of the gravitation equivalents of the Maxwell equations, but always thought, I need to find the others too. The theory of 1912 only takes care of static gravitational fields, and we will need more and other equations to keep to give an account of general dynamic gravitational fields. And the next step that Einstein looked for then is to, okay, so the first theory, the 1912 theory, is a theory of static gravitational fields. The natural next step is to look for field equations that also cover stationary gravitational fields. And one special case of that is, well, gravitational inertial fields. One special case of stationary acceleration fields are centrifugal and centripetal forces, right? Because there, the magnitude of the acceleration vector stays the same, but it changes direction. So it can be thought of as a stationary acceleration field, which would have a counterpart in a stationary gravitational field. And that's what Einstein started looking for. Now that he had extended the transformation group to uniform accelerations, which are static acceleration fields, take the next step and try to find stationary acceleration fields, stationary gravitational fields, and extend the transformation group further to that and find the corresponding field equations, as he had done before for the static case. Yeah, so I just said that here, just two quotes from the time where he says, so this is what I'm doing and I'm not getting very far. He said, in the second Scalar paper, it is not yet clear what form the general spatiotemporal transformation equations will have, because so far he had only extended the relativity group to cover uniform accelerations, and more had to yet be achieved. And when he writes to Michele Besso at the same time, telling him about this paper, in fact, sending him this paper, old friend from Bernheim's, in fact, colleague at the patent office, he says, I am still, you see that I am still far from being able to conceive of rotation as rest, right? That was one of his aims, be able to conceive rotation as rest. One question that comes up in the correspondence surrounding all this is already, and of course this will be a major factor for GR, how to represent the equivalent to the Faraday tensor, right? So the Faraday tensor, as introduced by Minkowski, is a four-dimensional matrix that has electric and magnetic field components. And Einstein at the time very clearly looked for a similar mathematical object that would have gravitational field and acceleration field components. Okay, we'll come back to that. But first, coming to track 2, which is Einstein's attempt, Einstein now, after all this resisting space-time, looking at Minkowski's line element in the context of his second scalar theory and looking, well, this does some work. So re-deriving the equations of motion of the second scalar theory that I've already shown you. But first I have to say the results that Einstein draws on there is Max Planck's development of relativistic mechanics. Max Planck doesn't get nearly enough credit for that, right? This Einstein's special relativity paper in a way does kinematics, and it was really Planck who developed special relativistic mechanics. In particular, in the 1906 paper, Planck used Lagrangian mechanics and the principle of least action to derive the relativistic counterpart of Newton's second law and the relativistic counterpart of Newton's first law as a special case of the second law. And this is what Einstein draws on and explicitly, against his otherwise bad practice, explicitly references in an addendum added to his second scalar paper at the proof stage, where Einstein noted that he could derive or rederive his equations of motion from the same Lagrangian that Planck had used to derive the relativistic version of Newton's first law. And that Lagrangian looks particularly simple in a four-dimensional form. Namely, the Lagrangian that he uses is just, so this is Lagrangian L, which is just a four-dimensional Minkowski line element expressed like this. However, now, right, we're in the context of his scalar theory. So the speed of light here is a scalar field that can differ from point to point. And this is already something that Einstein clearly is surprised. This is a bit weird, right? So this is a dynamical component, and all of these are static component. At the time, he says it seems to break the relationship between space and time, because now the time dimension here has a very different character from the three space dimensions. But he shows that using that Lagrangian, very, very straightforwardly, he can rederive his equations of motion for a field subject to the gravitational force, which is an interesting pointer, of course, right? This was supposed to be the equations of motion of a particle subject to a gravitational force, but he derives it from how Planck had derived Newton's first law, which is supposed to be the case of a particle that is not subject to a force, including a gravitational force. So here already comes the idea, maybe gravity is different. Maybe the distinction between being subject to a force and not being subject to a force doesn't quite apply in the same way. And this is the last sentence from this note, edit, and proof. He takes this already, sort of looks ahead and says, the Hamiltonian equation, this is how he calls it's a Lagrangian equation. He always says Hamiltonian for what we would today say Lagrangian. The Lagrangian equation just noted gives us an inkling of how the equations of motion of the material point may be structured in the case of dynamic gravitational fields. And indeed, later in the Wolf paper, he argues that this Lagrangian is exactly the Lagrangian that he should hold on to, but now with different things here. So just teaser. Okay, so this was part two, looking at how the equations of motion in the scalar theory can be rederived in a space-time context with a four-dimensional line element. The third path is about rigid bodies. And here too, there is major work being done by others than Einstein. Einstein really was not the leading figure of relativistic mechanics in these years, right? Others were doing it, most of them mathematically much more capable than him. He caught up later, but at the time, he couldn't have competed with Born, Lauer, and Sommerfeld in particular. And so these are the four people who guide this research. The question, what happens to the concept of a rigid body in the context of special relativistic mechanics? And interestingly, also this hasn't really been shown much in the literature yet. In the course of this, these guys use non-Euclidean geometry to describe the concept of a new concept of a rigid body. And the whole thing is spearheaded by Max Born, who gives a talk at the Salzburg conference in 1909, speaking directly before Einstein. And the two of them have a conversation afterwards. And Born notes that the classic definition of rigidity states that the distance between all constituents of a body does not change over time, right? That's what it means to be rigid. The distance between the constituents remains the same. But spatial distance is not an invariant of the Lorentz group. And so a body that is rigid, according to that definition, in one special relativistic coordinate system would not be rigid in another. And that was seen as untenable, right? If a body is rigid, that's pretty much a physically objective fact as you might have wanted. So Born developed a new infinitesimal definition of rigidity that gave partial differential equations that a body has to satisfy in order to remain rigid in a fully special relativistic context. And in doing this, or in his mathematical account of this, Born defined a four-dimensional space with a metric defined on it, and he writes it down like this. So this is the metric tensor of this four-dimensional space, and the metric can change from point to point. So it's the first appearance in physics, I think, of a dynamical metric on a four-dimensional space, and the body in question is rigid if the metric tensor does not change. So one has to be careful here, right? The metric in question is Riemannian, so plus, rather than pseudo-Riemannian, and it's designed to keep track of a particular property of a body, namely its rigidity. The metric is not supposed to be the metric of physical space. Instead, Born uses Riemannian geometry clearly as a tool to define a physical property, namely rigidity. And this will become important for Einstein, because I think Einstein ends up being much more flexible of what it means to be geometric and using geometry as a tool, always being very careful that just using something like this doesn't mean that physical space or space-time is such and such. In a way, he's sort of, one could say, much more like later fiber bundle geometers.
Sorry,
Yeah.
Small comment. Does it have any connection to the strain tensor, three-dimensional?
Yeah.
Local.
Yeah. Yeah. Yeah.
Four-dimensional Riemannian signature castle in the strain tensor.
Yes, indeed. And that will also be important in later connecting like Lauer's energy momentum tensor to the metric tensor that Einstein ends up using. Yeah. Okay, then, but so one thing that I wanted to emphasize. So here already at the 1909 Salzburg conference, Einstein sees Born using Riemannian geometry with the dynamic metric, even though it's not a dynamic metric of physical space or space-time. Also at the Salzburg, Riemannian, yeah. Also at the Salzburg conference, yeah.
By dynamic, do you mean just
well, it can change from point to point. That's what I mean. Can be zero at one point and non-zero at another point. Yeah. Also at the Salzburg conference, Sommerfeld uses positively curved non-Euclidean geometry to rederive the relativistic law of velocity addition. So he argues, right, velocity addition is quite messy in the way Einstein derived it, but if we use a positively curved non-Euclidean geometry, everything comes out beautifully. And I'm just mentioning this again, non-Euclidean geometry used in a very instrumental way, not as a property of space, but defined on an abstract space that allows Sommerfeld to rederive the relativistic law of velocity addition. So in the context of the pushing the new relativistic concept of rigid bodies, Einstein encounters Riemannian and curved geometry in more than one way, which leads us to the rotating disk argument, track 4. And that appears already in the first Scalar paper, where Einstein notes that if you have a disk, right? So this is a disk. The circumference of the disk in that particular frame of reference is 2 pi times the radius, and in a frame of reference that is at rest. Now, if you go to an accelerated frame of reference, then because of length contraction of the elements along the circumference and missing length contraction, never mind, along the radius, because the radius elements are perpendicular to the direction of motion, the circumference would be bigger than 2 pi times the radius. And this leads Einstein to argue that that geometry is relative, that whether the laws of Euclidean geometry hold or not depends on the coordinate frame, on the frame of reference. And he also spells out both here and in another manuscript of 1912 what he means with geometry. Geometry is about what bodies do, right? It's not about what's the properties of a space. Geometry is you can say something is Euclidean or non-Euclidean if you observe how bodies behave, how they can be arranged and move, and if they move in such a way that the laws of Euclidean geometry are broken, then they move in a non-Euclidean way. But this is a property of the bodies, not of an underlying space, at least how Einstein sees it. This corresponds to how he presents the rotating disk argument in 1917, where he says, this proves that the propositions of Euclidean geometry cannot hold exactly on the rotating disk, nor in general in a gravitational field. So what he's saying is a gravitational field will cause physical bodies to move in a non-Euclidean way. He's not saying gravitational field is really the geometry of a non-Euclidean space or space-time. Stachel interprets, yeah.
Previously, it was all three geometry.
Yes.
So
this is still three geometry.
This is 1917. Is he talking about three geometry?
Yep, still. I mean, it's writing 19, but he speaks of the rotating disk using again three geometry, but he transfers the argument that I just made to four geometries later. But yeah, it's an important point. A rotating disk is a three-dimensional argument in a way. So Stachel interprets this as saying, if my reconstruction is approximately correct, we can see that Einstein's recapitulation of the rotating disk story will not only represent a certain logical order of presentation of the material leading up to the recognition of the need for a non-flat space-time structure to describe the gravitational field, but would also represent a fairly accurate historical reconstruction of Einstein's own journey. I agree with almost everything that Stachel says ever, but this yellow part here, not quite. I think Einstein did not see himself as having recognized the need for a non-flat space-time structure to describe the gravitational field. Instead, he saw himself as having found that in gravitational fields, when subject to gravitational fields, bodies do not behave according to Euclidean geometry. And this is a big difference because the question of whether Euclidean or non-Euclidean geometry holds only enters the picture once bodies enter the picture and are influenced by gravitational fields to arrange themselves in this way or that. In the absence of bodies that behave in a Euclidean or non-Euclidean way, there is no question of whether things are Euclidean or non-Euclidean. Okay.
So, about light,
What about it?
would be included in bodies, like we're talking about the sun portion of the light rays?
Yeah. Yeah, I think he would include that in this narrative. That I mean, I think let me come back to it, because it is true that once he has a four-dimensional geometry, he speaks about the light rays being curved, and in the end it comes to the question of the interpretation of the equations of motion and this link to Newton's first law, the law of inertia, and that would apply to light rays. I'll come back to it. Julian.
This is really probably for the discussion afterwards. To what extent was he perhaps thinking already of Poincaré's ideas about geometry and rigid bodies and so forth? Yeah, I mean, he has the paper in 1921 or 22,
yeah,
Geometry and Experience.
Yeah.
Was he perhaps already influenced by Poincaré? Because he read Science and Hypothesis when it came out, didn't he? And
yeah.
said he was read it with fascination. I mean,
yes, I think it's clearly direct influenced at that time already. First, as you said, because he read it earlier, but also the well, what I said here, geometry is about what bodies do, and there is a certain relativity of geometry, and thus also conventionality of geometry. That's something that he says in the 1921 Geometry and Experience, but there's a manuscript from written between 1912 and 1914, where he makes the same point. In fact, makes the point even a bit better than in the Geometry and Experience point, and also draws the connection to Poincaré.
and does he mention Poincaré in that early paper?
I'm not sure if he mentions it by name. But it's an unfinished manuscript, right? So yeah. Okay. Now, fourth path, again, rooted in the further development of special relativistic mechanics, which brings us back to Sommerfeld. Sommerfeld, drawing on the work of his close friend of Minkowski, who had just died, generalizes vector analysis and vector algebra to 4 dimensions and introduces the general notion of a tensor in this context. There had been the concept of a tensor had been present in solid state physics, but Sommerfeld brings it to this context of special relativistic mechanics in his attempt of developing a systematic vector analysis and vector algebra. And he defines a 4-dimensional tensor as the product of a 6-vector with itself. A 6-vector is what at that time called the types of objects that we now would call the Faraday tensor. It's a 6-vector because it has 6 independent components, right? A 4-vector has 4 independent components. A 6-vector has 6 independent components. And if you don't write the Faraday tensor in a matrix representation, it makes perfect sense to think of it as a 6-vector. So a general 4-dimensional tensor is defined as the product of a 6-vector with itself. Yeah, set with itself. And Sommerfeld also shows that a general 4-dimensional tensor has 16 independent components, which reduce to 10 independent components if it's a symmetric tensor. So if there's a permutation invariance in the indices. And this is what then Laue, who was doing his habilitation in Munich, where Sommerfeld was chair at the time, And Laue, on the one hand, builds on his mentor Planck, and on the other hand, on his new boss, slightly less good relationship, Sommerfeld, and develops what he calls a world tensor, which is a particular type of Sommerfeldian tensor, namely a four-dimensional tensor that is symmetric in its indices and that obeys a law of this form. And Laue gives general arguments that the interpretation of the components of such a tensor, which can already be found in Minkowski for the special case of the electromagnetic field, have a general meaning, can be transferred to any material system, so that you have energy density, energy current density, momentum density, and momentum current density, which is the old stress tensor from solid state physics, all embedded in this one form. And he gives convincing argument that that object gives everything there is to say about the mass and energy flux of any material system.
This is right?
Yes, also. Yeah. Pseudo-Riemannian, yeah. Now, Einstein was aware of this work of Laue from 1911, which we know from a couple of reasons. One is that after, yeah.
This nabla here, is it, what are you thinking of it as the special relativistic?
Four-dimensional divergence. Yeah.
But for Minkowski, just Minkowski.
Yeah, absolutely. I mean, using later terminology, this the affine connection to which this covariant derivative corresponds is Minkowski spacetime. There's no inkling here of a dynamical pseudo-Riemannian metric, but it's all four-dimensional. Okay, so as I said, so Einstein had got his first professorship at the University of Zurich in 1909, then left for his first chair at Prague in late 1911, and then came back to his alma mater, the ETH Zurich, in the summer of 1912. And at the time, the chair of the department, Alfred Kleiner, asked Einstein for recommendations of who could be his successor at the University of Zurich. And Einstein recommended Laue and wrote, Laue is, in my opinion, the most important of the younger German theoreticians. His book on relativity is a real little masterpiece, and much of it is his own intellectual property. Laue is a man of definite formal talent from whom much good is still to be expected. After that, he says he also has the reputation of being a terrible teacher, but whatever. And so we know Einstein knew Laue's book and thought of it as a masterpiece. And in that book, Laue introduces special relativistic continuum mechanics, including the general mass energy momentum tensor. And then when Einstein came back to Zurich, well, they were neighbors, right? Laue was at the University of Zurich. Einstein was now at the ETH, which is only a 10-minute walk from each other. And Laue was working on the second edition of his book and developed the theory of energy momentum tensors and relativistic continuum mechanics significantly more in the second edition, while Einstein was his direct neighbor. And so this brings us now to a point where sort of things are starting to draw to a close, right? So we have from track 2, which was the equations of motion bit, we know that Einstein has already thought, in the context of my static theory of gravity, I can, if I look at Minkowski's line element, I have this Minkowski metric, but modified in such a way that the 0,0 component is my static scalar field, right? We're already, and he comments at the time, it's a bit weird because it makes the space components and the time components to be quite not alike. So already here, that by itself, he might have thought, well, how would it be if not just the 0,0 component, but all components depend on, can vary from space-time point to space-time point, And now via track 4, he has learned from Laue that the most general way of expressing mass energy equivalence and the source of gravity, well, we argued, right? The source of gravity has to be all forms of mass and energy. The most general way of expressing this source is a 10-component object, T mu nu, derived by Laue. And so he knew the source of gravity has 10 components, suggests the gravitational field itself should also have 10 components. Well, and there is already a 10-component object that I have related to gravity in the addendum to my 1912 paper with only one dynamical component, but Laue here of everything is dynamical, of course, can vary from point to point. So from here, I think it's only a really quite small step from saying, well, maybe this is the source of gravity, and this is the gravitational potential, special case static fields, general case, all components of this tensor are dynamical. And this is the point, final path, final track. At this point in time, Einstein moves back to Zurich and rekindles his relationship with Marcel Grossmann, who was his savior more than once in his life. First, helped him pass the exams by giving him his lecture notes, which Einstein didn't attend the lectures himself, took Grossmann's lecture notes. Second, got him the job as a patent clerk in Bern after Einstein had been unemployed for 2 years. And now Einstein returns to Zurich and says again, Grossmann, you must help me or I'll go crazy, according to report of another fellow student, Koros, with whom they both were undergraduates together. And this is, by the way, this is the lecture notes of Grossmann from when they were undergraduates of a 2-year lecture course on infinitesimal geometry and invariant theory, which both Einstein and Grossmann had to pass exams for, and which Einstein later described as the most beautiful lectures he had ever visited on differential geometry, specifically on Gauss's theory of curved surface. And there in the lecture notes, you see this is a sort of the line element of a two-dimensional surface in Gauss's theory, which Einstein thus must have been familiar enough to pass the exams, learning using at least Grossmann's notes.
So that is Grossmann.
These are Grossmann's notes, yeah. Beautiful handwriting, right? Yeah. Yeah. Okay. And I'm almost done. In a autobiographical sketch from 1955, which is much, much less known than his autobiographical notes from 1946, Einstein describes what happened when the stage he was at when he came back to Zurich. He said, the decisive thought regarding the analogy to the Gaussian theory of surfaces I only had after my return to Zurich in 1912, summer of 1912, without knowing at first the investigations of Riemann, Ricci, and Levi-Civita. I was only alerted to these by my friend Grossmann in Zurich when I put the problem to him to find generally covariant tensors whose components depended only on the derivatives of the coefficients of the fundamental quadratic invariant, i.e. the four-dimensional metric. So he claims he had the question ready to put to Grossmann, right? I need to know more about tensors, which were only just introduced by Sommerfeld and then Laue into relativity theory. And he remembered that he had put the question to Grossmann thus. And then they started to work on finding such a theory together. Now, what do we learn from all this? I think there's two core lessons. The first is that in Einstein's way of thinking, physical geometry is about how bodies move, and they can move differently in different coordinate systems, right? So in one coordinate system, they move in a Euclidean way, and another coordinate system, they move in a non-Euclidean way, three-dimensional in that case. But everything that goes beyond that, everything geometrical that goes beyond how bodies move, including the geometry of a four-dimensional space-time, and the later geometries in unified field theories, all of those Einstein thinks of as mathematical tools to be used in a fruitful way, not as something that should be too quickly interpreted as having ontological significance. So on the one hand, he has a very narrow, almost deflationary notion of physical geometry, and on the other hand, a very wide view of what counts as geometrical in a mathematical sense, something that could be used. And I think this is how he thought of using pseudo-Riemannian geometry in the context of general relativity, not as showing that gravity itself is the curvature of spacetime or the geometry of spacetime, but it's non-Euclidean geometry, pseudo-Riemannian geometry is a mathematical tool used to give an account of unified gravitational inertial fields. So what can we learn from this philosophically, just to finish up? So I think with what I told you, at least in Einstein's head, I think you can see that the path from the scalar theory defined on a three-dimensional space to the theory of a metric tensor on a four-dimensional spacetime, curved metric tensor on a four-dimensional spacetime. In Einstein's mind, this was not a big ontological step. This was a continuation of thoughts he already had. In fact, many of the ideas that he had that he used in his interpretation of GR have its roots in this previous theory. And he's very explicit about this in the involved theory with Grossman and in later publications. In both cases, he thinks of these as two theories that are theories of a unified gravitational inertia field. And geometry only comes into it as soon as you consider bodies, or if you look at mathematical representations. He believed that none of what he did was a change in ontology. So he had the position, I think, that all talk of the geometry of spacetime, and he made this when Laue, especially in the 1940s and 50s, attacked him on this, and he stick to his guns. He believed that all talk of the geometry of spacetime is dispensable, given that we could all, as well and more accurately, talk of gravitational inertia fields and how they influence bodies. And in the long run, he even believed that the distinction between spacetime geometry on the one hand and material bodies on the other hand should be overcome in favor of an ontology based entirely on fields. And both what we think of as space-time geometry and what we think of as physical bodies should appear as solutions to unified gravitational inertial electromagnetic field equations. So I think the general lesson I think that we can draw from this is that there is not just a context of discovery and a context of justification, but also a context of interpretation, right? Because what this shows is that there is more than one possible interpretation, more than one ontology that you can associate with a given mathematical framework like this one. And I think if we see only one possible interpretation that we believe we can read off directly from the math, then we don't see enough. And also, I believe that not going through this exercise and looking at the context of interpretation and developing different possible interpretation, we would be the poorer for it, because we would miss a very important transition that happens much later, namely in the 1950s and 1960s. That's when the real geometric ontology of GR really comes about, trailblazed by John Leighton Singh, who in his book of 1960 said, if we accept the idea that space-time is a Riemannian force space, and if we're relativists, we must, then surely our task is to get the feel of it. And the first thing we have to get the feel of is the Riemann tensor, for it is the gravitational field. If it vanishes, and only then, there is no field. In Einstein's theory, either there is a gravitational field or there is none, according as the Riemann tensor does or does not vanish. And this, I think, so if you read this while you're studying GR for the first time, this looks as if, well, clearly this is right. Obviously this is right. This is the only sensible interpretation of the formalism. But I think what the history shows us, well, it might be the best interpretation, but it's not the only one. And seeing them in comparison can teach us a lot. And in particular, it allows us to appreciate the difference between antiquity and Renaissance, right? If you think of Einstein and his contemporaries as the great time in general relativity that corresponds to the times when Plato, Socrates, and Aristotle walked the earth, very important time philosophically, but also very important, the Renaissance. And if we don't see these distinctions and possible different interpretations, then we can't see the difference between antiquity and the Renaissance, and we would miss out on the important new interpretation and mathematical innovations that Singh was a trailblazer for, and that eventually made possible bring about the Leonardo of general relativity. Thank you.